Hello all. So yeah, I've just read that Concordia is reassessing its policy to go back to in-person teaching, so it might be longer than expected. Well, we'll make up for it. By the way, I forgot to say that, but yeah, two things I forgot to say before, so I might say it right now in the discussion. 2 points. So one, so I'm not forcing anybody to do it, but if you don't mind, it would be nice to turn your camera on. So if you're in underwear, I don't want to see anything, but if you just, yeah, that would be just to have some interaction, just to see a few faces. So it helps me a lot to see if you're on it or you're lost or you're confused. So that helps a lot. Second point about emails, forgot to say. So you may have realized that I'm teaching more than one class at Concordia in teaching environment and microeconomics. So it helps me a lot if you write me to just say, hi, sir, could you, yeah, I'm a student in your Econ 325 class. It's an awesome class. I'm having a good time. I'm enjoying this. You're the best teacher. And this is my request. So that would be very helpful too. So just start by saying that it's a 325 class, so that saves me some time. Yeah, so two small points I forgot to say. All right. So yeah, are there any questions before we start? No, all good? All right. Yes, so of course, TA sessions don't start now, so we still have some leeway to make headway in the material, but we can't take too long because they're going to start soon. So here we go. So let's go with sets again. So you might remember last time we had seen sets like the natural numbers, the integers, the rational, the reals, the complex. So these are large sets of numbers that we use as often as a universe to describe some problems. R square is a very popular one. So as you're going to see. All right. So sets, what are they? Yeah, so today lots of definition. So that's the thing with math, we have to be precise. So sets, they are a collection of objects that can be defined by in different ways. So one is definition by enumeration. So you could say that the set S is the set. So we use curly braces for that. And we can say it's 1, 3, and 5. All right. So that is a set. Now, does the order matter for sets? Can somebody say something just in case my sound isn't working again?
Yeah, it's working.
Okay, thank you. Yeah, thank you. It doesn't matter. So order doesn't matter. So we can write, for instance, 135 is equal to this other set 315, right? And the sets can also be described by a description or a definition. So let's see, this is one way to do it. Another way to do it. Definition by description. So what you can say is, for instance, sets integer larger than 2. So we would write something like n equals, or rather, yeah, s equals x, and then this is such that so s so that x is this is, oops, yeah. This means is an element of, so what did I say? Integers, yes. Or yeah. It's an element of z, and x is greater than 2, or larger than or greater than. And so here you notice that I use the word and. So there are symbols in mathematics to substitute a word like and. It's I think it's a symbol like this one. So it's a line that like this and line like this. But yeah, they don't use this in the book. So I don't think we should formalize ourselves with that. It's not really widely used. Right. And yeah, of course, this is greater than, and this is greater or equal than. So yeah, I'm defining a lot of stuff. Usually that's something that you probably know already, but just to be sure. And of course, if there's any uncertainty, don't hesitate to ask me. All right, so let's try another one. So other examples, so reals. Then let's say strictly between -5 and 5. So I would have, well, let's call this just to, for fun, let's have different letters. So that's our third example. So S3 equals, and then in the book, so what I've, not sure I like it, but that's what they do in the book. So when they take numbers that are real, then they usually omit what set they are in. So they would say something like simply x such that -5 smaller than x smaller than 5. So if the variable is part we can omit it. Of course, it's perfectly fine to say that x is in the reals, and so this is perfectly fine too. So I'm going to stick with the thing is in economics, we really usually have real numbers. We use real quantities. So it's not that big a deal to omit it if it's clear from the context. But if it's not in the real numbers, then really say it. Otherwise, it might be confusing. All right. So and then here I said, yeah, strictly between -5 and 5. What do I mean by that? I mean that it cannot be 5 or -5. Yeah. All right. So question. So yeah, so well, let me introduce another. R is the real numbers. Yeah, real numbers. So thank you for the question. It helps everybody. So 3, 4, oops, 4, 5, -2, 3, 4.1, pi, √2. These are all real numbers. Okay, now other notion, subsets. Yeah, let's just say subset. I think I wrote this one. Yeah, so means is a subset. And now in math there is some, so it's funny how mathematics has to be very strict. Everything has to be very strictly and precisely defined, and yet there are varying conventions. So people don't always agree with what a symbol means. So in the book, this means that some set is a subset of some other set, meaning that the element of the first set to the left are also all in this set to the right. But some people say that this means that it's strictly a subset, meaning that it cannot be the same. And if the two sets can be the same, then people use another symbol that I can find maybe. Yeah, that one. Yeah. So is a subset or yeah, is weakly a subset. It can also the same set. Okay, so yeah, so this I'm going to put this in brackets because that's not the way we're going to, yeah. Some people use this symbol as is weakly a subset, meaning it is a subset with fewer elements, or can also be the same set. But here we're going to use this to mean this. So all its elements are included in the other set, and it may be the same set. All right, so that took some time, but so was that clear or not? So this is just a matter of so in the book they use this symbol to mean is a subset, and what this means is 135 can be a subset of 315 using this symbol there, because all of the elements 135 are also in the element of this set 315. But of course, you could also have 4 here. All right, and some people would mean that this symbol is you strictly need fewer elements in this set than this other set. I'm not going to. I'm going to use this as meaning this. All right. So, question just to see if if I'm being clear. All right. What was my? Oh yeah. So is. Yeah, I think I cannot ask my question. Can I? Oh yeah. Is it true that S1 is a subset of S3? So S1 is this set, and S3 is this set, or rather, yeah, this. No? All right, so why, what element of S1 is not in S3? Oh, you're right. I thought it last time, and I use the weekly included. Yeah, I use smaller or equal. So my answer was yes, and then and then I thought, oh, I made a mistake, but no. So you're right. No. So to check that, you check whether all elements in S1 are also obey the definition of S3, or if yeah, so if basically you check element by element of S1 if it's in S3, or if the definition of S1 matches the definition of S3. So here, what's wrong? No, because 5 is element of S1 and 5 is not element of S3, right? So no problem with this, this set of definitions. So that's, I haven't really introduced anything super complicated. It's just setting ground. All right. So next question, next element, empty set. So you could also write this equals to, this is just a collection of an empty collection. There's nothing in it. But yeah, use this. This is better. So question is the empty set a subset of R3, of not R3, S3. So this is, so take a guess. This is a matter of, yeah, I'm going to say it, but tell you it's really a matter of more of definition of what how sets work, but yeah, use your intuition to take a guess. Yeah. Yeah, so it's that was my point. My point is, what do you do with the collection of nothing? Can nothing be included in something? Usually when you say something like, oh, you have a nice collection of cars and I have the same collection but with fewer cars, then you wouldn't qualify having nothing as having a subset of that collection. But yeah, in math, yes. So yes. So what we could say is the subset is the empty set is a subset of any set. So I would just write it down. Yes. The empty set is a subset of any set. All right, so now subsets. So yeah, question. So given that, what I just said, that subset that the empty set is part of any set. So what are possible sets of S1 Yeah, you can write it in the chat if you like. It's possible. A reminder, S1 is this. Oh, so explain again this empty set. So empty set is just nothing. And nothing is always a subset of anything. That's a very philosophical statement. Extremely abstract, but yeah. I don't have taker for my question. All right, so let's do it. Somebody writing it right now? Or not? Bless you. All right, so the subsets of S1s, S1 are, so you can have the empty set, which is a subset of everything. I can have, so what was S1 again? So let's just put it here again. So I have 1 is a subset, 3 is a subset, 5 is a subset, 1, 3, 1, 5, 3, 5, and 1, 3, 5. So the whole set S1 can also be a subset of S1. All right. So question. Yes, absolutely. Because the empty set is a set, and a set can be a subset of itself. So the empty set can be a subset of the empty set. Absolutely, good question. For set of n elements, how many subsets will we have? Now it's now you have to start thinking of it. No, 0 is not contained in the empty set. 0 is a nice integer, and the empty set doesn't contain anything. So n subset. Well, the first thing we can do if we, so I have a proposition that the set of n element has n subset. Oh, another one, n squared. Yeah, I prefer n squared. So just to check the first, if whenever you have an idea, well, you can check with some examples. So this is something that I think may be scary, may make mathematics scary in general. It's that mathematicians, they come up with super simple statements that are very hard to grasp because they're so abstract and general that it's hard to wrap your head around it. But what you have to know is that it's not how mathematicians work. So they really start by saying, oh, this is interesting. I wonder how that works. Well, let's start with an example. And then let's continue with another one and another one. And when they try 10 examples, then they look at everything they have done, and they think, okay, is there some general rule that I can start thinking about and proving stuff with? But you have to start with examples. So here, let's just start with an example. So we have a set S1 that has 1, 2, 3 elements. How many elements do we have? Well, we already know that we have subsets 1, 3, and 5, but we also have all these other subsets. So no, it can't be that you have n subsets for a set of n elements. But so I have 3 other suggestions: 2 to the n squared, and n squared plus 1. All right, so let's just apply it again. So how many subsets so we have 3 elements, and we have 1, 2, 3, 4, 5, 6, 7, 8. So 3 squared would be 9. So n squared is not good. N squared plus 1 would be 10. That's not better. 2n plus 2, 6. Yeah, 2n plus 2, maybe it works. Let's try another example then. Let's try 1 and 3. Subsets are empty set, 1, 3, and 1, 3. So that's 4. So 2n would be 4 plus 2, 6. So that won't do. But I have seen the right answer. It's 2 to the n. And let's check it out. So we have 2 to the 3 is 2 times 2 times 2 equals 8. And we indeed have 8 elements. And here 2 to the 2 is 4. And indeed we have 4 elements. So the answer is 2 to the n subset. Why? The genius who have proposed this suggestion, Mr. Demetris Bakopa.
It was a lucky guess.
Good. So can somebody think of the reason? Or maybe that's not the right answer, and if we try 16, it's going to fail. But no, I assure you it works. Because yeah, it's true. We have to include the empty number. Yes. All right. Perfect. Michael Richard. Yeah, that's the best reason. Each element can be included or not in a subset. Hence, 2 possibilities for each element. So let's start with if we start with this, then there's only one subset, which is this one. Then we add an element to this set. So we have 1 here. And what subsets do we have? We have, so we added 1 extra element, So that element can be either in all the subsets we had or not in all the subset we had. So if I only add one subset, so I can have now two subsets, either one with one or without one. And then let's add another one for just for fun, 1 and 3. So I just added one element, so I can either include it in these or not include it in these, because these are, of course, subsets of this larger set. So I can have them without it and them with 3 added to it. So every time I multiply by 2 the number of potential subsets with every element. I could write down a more formal. So this principle is what we call induction, and it's a super powerful method in math. So how you prove stuff by, oh, there's somebody. So for an empty set, we can have one subset, which is the empty set. Yeah. The empty set has one subset. Yeah, so just a comment on this with reasoning. Exactly, to the 0 is 1. So comment. So this is way more advanced. You don't need to know that, but just in case to and this style of proof. By induction. Start with a simple case. Say we start with this. Show that it works. And then show that if it works, like a simple case with, let's just say with 0 elements here. And then show that if it works for n elements, it works for n plus 1 elements. And then once you show this, then you can be sure that it's going to work for an infinite number of elements as well. So this is the sort of, basically what we show is however many steps we do, we're always going to double every time. It's useful in computer science. All right, but this is an aside. I'm not going to ask you anything about this. I'm going to put it in bracket. All right. So where were we? Oh, yeah. Now let's have some fun with operation and sets. Union. Oops. So okay. A set is for a set formed by the elements in either of 2 sets. So for instance, if I have the set X such that X is element of 1, 2, 3, or X is an element of, let's just say, 3, 4, 5, 6. Then yeah, no, I don't need this. Sorry. And then we can write that how did I write it? Yeah, no, that was fine. It's just I was missing. Yeah, so a set formed by these two sets. Yeah. So this is equal to simply union of these two things. And it's also equal to 1, 2, 3, 4, 5, 6. All right. So that's 3 ways of writing the same thing. So a set form, a set for which either elements are part of 1, 2, 3, or elements are part of 3, 4, 5, 6 is exactly the same as 1, 2, 3 union 3, 4, 5, 6, and it's exactly equal to what? 1, 2, 3, 4, 5, 6. Intersection in not either of two sets, but in both sets, in two sets. In both, yeah, of two sets. I think it's the more clearest way of writing it. So then we would simply put and here, and this would be equal to intersect. And then what would I have here? Oops. Yes, thank you. Some other definition, universal set. So universal set is it's like, yeah, it's the universe we care about. It's where we are. So it's the elements in the universe. Yeah, no, sorry. It's a set of all considered all elements under consideration. And why do we define this? What is it useful for? Well, it's useful to know what is outside of sets. So if I care about some universe of numbers, and I have one set in this universe, which is 1, 2, 3, then I care about what are the elements that are not in this set, for instance. Yeah, so we can say that. And it can be anything. It doesn't have to be like the reals or the rational. It can be just, if you can say, all I care about is the universe of these 4 elements, 1, 2, 3, 4, for instance. So you say whatever I'm defining, whatever I'm discussing, it's always going to be using only these 4 elements. That's all there is. And finally, complement Let's put some space there. Yeah, that's a good question. And yes, empty set is part of anything. So it's part of any universe. Yeah, and finally, complement. Yeah, let me use this. So universal set, well, it's really take this sentence. I think it's a very neat sentence. But so it's going to be very clear when I talk about complement. It's just if I say something like, let's consider the real numbers, then anything that's not inside a set, so that's whatever is inside the real numbers, but not in that set, for instance. Shouldn't the intersection set also include the empty set along with 3? So yeah, no, I'm not talking about all the subsets of things now. All I'm saying is, what is the intersection of these two sets? The intersection is formed by any member that is in both sets. So it's a set, it's not an empty set. Well, it could be. So you could have, let's just say that I could have 1, 2, 3 intersection with 5, 6, 7. And what would I get? I will get nothing. I would get empty set. Yeah, I'll. So it's going to be very clear when I talk about complement. So yeah, so I can't use this symbol there because really all I care about is describing what is the intersection. So it's not empty because 3 is common. But if the intersection is empty, then I get the empty set. Yeah, so complement, so elements in the universe. So these two really to go together, universal set and complement. So it's I understand that this definition looks strange given that we don't know what it's for, but now I'm going to show you what it's for, so you're going to understand why I'm wasting time talking about this, or not wasting time, using time talking about this. Elements in the universe, but not in a set. Noted like this. So with that tilde on top. So yeah, so like this. So if I have, let's use what I got here. U is and a set, let's say S4 equals 2, 3. Then S4 is going to be what? Yeah, 1, 4. Does that make sense? So I need to define what my universe is in order to use this operation. If I don't have it, then I have no clue. I don't know, maybe a 6 is in there because it's in my universe. As long as it's not inside 2, 3, I could have anything. So I have to define what the rest is. So this is what it's for. Okay. Oh yeah, I could also write it this way. So it's also equal to, let's use definitions. So X such that X is an element of U and X is not an element of S4. That's a way, another way of writing it. And the question for you, what is the empty set of, what is that? Oh, I kind of gave it away, but still, what is the complement of, of U? Yeah, but in that case, yeah, exactly. I said all the elements I care about are 1, 2, 3, 4. So all the elements that are not 1, 2, 3, 4, but that are under consideration are nothing at all. So it's the empty set. Right. So now that your brain is warmed up, let's continue with some a bit more challenging stuff. So let's go ahead. Commutative là. So commutative là is a property that an operation can be made in any order and will give the same thing. So A union B is equal to B union A. Yeah, and for those who are geeks about math, so what we say when commutative law works is we say that these are part of abelian groups. Named after a mathematician, I think he was Scandinavian, but I can't remember his country. So can we say that A inter B equals B inter A? So I'm just going to put a question mark there. So can we say that? No. So I'm going to tell you one not necessarily. So you're saying that, say for instance, here I get the empty set, but if I flipped it around, I might not get the empty set, for instance. So I'm going to give you a very good proof strategy to show that something is not true. So you don't have to take a huge amount of steps. All you have to do is find a counterexample. So find an example for which it doesn't work. And here I challenge you to find an example for which it doesn't work, because it's, I think Yeah, yeah, we are all wrong once in a while. Don't worry. All right, and another more complicated law, distributive law. So I have a. Oops. Yeah, so one thing I should so laws, consider sets A, B, and C. So we know we're talking about sets. It's always good to say that. Distributive law, A intersection B intersection C. Is that equal a no, this is the associative law. Wow, what my notes are wrong. I'm just looking at this and yeah, this is associative law. Should really correct this for next time because yeah. So is that the case or not? Take a guess. Let's try an example. So I have a. So anytime you're given something that's super general, what you have to do is just try stuff and see what happens. Does it look right or does it not look right? Sometimes you may try something for 10 example, it all works, and then but you just got lucky and the 11th one doesn't work, but it's the exception. Normally, if you try it a few times and it looks like it's working, then you can bet that it's probably all right. So let's have A equals 1, 2. Yeah, I can. Let's have. Let's always use the same. A equals 1, 2. B equals 2, 3. And C equals, I don't know. Thing is, sometimes it can, maybe I'm not choosing well my numbers and we can't say a lot about it, but all right. Yeah, it looks the exact same. So yeah, it's true, but let's verify it. Okay, so let's go ahead and check this. So, oh, by the way, something I haven't said, but what's inside parentheses you do first, just to be sure. So this is equal to 2, 3, 3, 4. So intersection of 2, 3 and 3, 4 is just 3. And the intersection of these two is empty set. Yeah, so it looks like, and yeah, we can see that here what we're trying to see is to find is something that's inside all 3. And as you can see, here you have 3 that's common, here you have 2 that's common, but it looks like yeah, you don't have, yeah. Okay, so A and C have no common elements, so it doesn't look good, but still we can try. And I'm going to show you how to do it more, yeah, to do it more convincingly, I would say. So the exact strict, so I want to give a flavor of what it is to demonstrate stuff. But if a mathematician, a real mathematician was looking at my work, he would say, no, but it's not, you're not being formal enough and thorough enough, and you have to. So I'm not a mathematician, I'm an economist, and I'm there to really help you mostly. So not hopefully. So not to torment you with formalism. Okay, so. Oh, but I wrote the same thing there. Okay, sorry, my goal. My goal was to use this, to write it this way. Oh, you should have spoken out. Now I'm. So this is something that equals to something else is indeed equal to that thing. So yeah, that was what I wanted to do. So can we change the order of the operations there? So this is equal to, so A is again 1, 2, 2, 3, 3, 4. So it might look trivial what I'm doing, but check it out anyways, because this is the kind of thing I may ask you at the exam, like verify that the associative law works for this case, for instance. And then what you have to do is just, okay, is that true? Let me check the first case. Let me check the second case. Yes, in this instance, it works. It's not a proof that it's going to work always, but still it's something that's interesting to try. All right, so here inter is 2. And oh yeah, sorry, the set 2. And there are no common elements between 2 and 3/4, so I get the empty set. So yes, the associative law, well, it works in that case, but yeah, take my word for it, it works all the time. And then the more complicated one, and another one, so it works for union as well. And can we mix union and intersection? I think we can, but I have doubts now. I think we can. Or no, we can't, I think. Check it out for yourself. Can we do that or not? I'll check it for next class too. Let me just think about it for a second. I haven't tried all of them, so. So imagine that I have Yeah, no, it doesn't work, I think. Yeah, it works in that case, but I think it doesn't work in general. So imagine that you have an element A that's A and C are have a common element. Yeah, okay, yeah. So no, it doesn't work. So to show that, so proof by counterexample. So let's have so let's have is wrong. So I just want to make sure that nobody gets a wrong idea. So imagine the simple thing. So A equals, so I'm just going to use very simple thing. So 1, so yeah, 1, B is empty set, and C is 1. So here I have 1 empty set and 1. So in that case, I get this equals to empty set intersection 1 is empty set. Oh yeah, no, it works. Oh no, I think it works. Oh, I thought wrong. Yeah, so it gives us 1. All right, so it probably works. So sorry, I'm not going to write this. Yeah, it's I've tried a bunch of examples from the book, but I really haven't tried them all, and now that I'm seeing them, I want to know whether it. I think it always works. So I'm still going to keep the question mark there, but take it works. We'll think about it. Okay. Yeah, I thought so. Just to finish this example, so I get 1, and here I get what? And then this is equal to 1. This is equal to 1, and 1 inter 1 is 1. Yeah, so it's the same. Sorry, this is a set. You think so? Naftej Singh Sohi. So what are you thinking about these 3? 1, 2, 3, 2, 3, and 3, 4? Okay, let's try it. All right. Okay, I didn't plan on doing this, but now that I'm looking at this, I had to try it. Okay, so so what did I want to try? A union B inter C. It's A union B inter C. So this is 3, and this is 1, 2, 3. Okay, and this. Yeah, I think, yeah. I think my intuition was good that it couldn't work, but I chose a bad example. So here I get 1, 2, 3. Enter 3, 4. Yeah, okay. So fine. So and here I get I get 3, 4. So okay, it doesn't work. All right. So my intuition was correct. It's just that the example I tried was wrong. So doesn't equal. All right. So this proof is not a proof because it looks like it works in that case, but yeah. So did I make a mistake in any way? 1, 2, enter, union, 3, 4. So enter is 3. So 1, 2, union 3 is, oh no, yeah, 1, 2, union 3 is 1, 2, 3. Then 1, 2, union 2, 3, enter 3, 4. This is 1, 2, 3, and then enter 3, 4. That's just 3, 4. Yeah, okay. So we have, and this is a real proof. You just have to show this, and if you want to prove this statement, that's all you care about. You just need a counterexample. What is just 3, the last one? Oh, yeah, you're right, the last one. Sorry. Yeah. Still it stands. Thank you, Tyler. Oh, wow, I've spent much more time on this small thing than I thought, but let just introduce the last bit still. So what was it? Yeah, distributive law. Yes, exactly. So proving that something is true is usually difficult, or it can be if you have a very simple statement that's basically almost an example, and you just try it out and you see whether it works or not. But if you have a very general statement, then showing that something is true, it can be difficult. But showing that something is not true is quite easy, because as soon as you find one counterexample, then it's okay. Because writing this is, I claim that for any set A, B, or C. Yeah, so I shouldn't have written this there. So this is example. Yeah, all right. So yes, for any set A, B, and C, then A union B union C equals to A union B union C. So this is, so then what you're saying is that for any A, B, or C, it works. So if you find one that doesn't work, then you're good. Then you know that. Then you know for sure that that the statement doesn't hold. Yeah, so we're almost done, but I'm just going to state the distributive law. So if I have A union yeah, it looks like the previous statement actually. So it's not equal to this, but it's equal to this though, or perhaps yes, perhaps not. So A union B enter A union C. And the opposite, A inter B union is equal to A inter B. A inter C. Yes, so just to restate what I said. So to show that some statement is wrong, it is enough to provide a counterexample. If you show that it's always wrong for anything, then it's fine. But as long as you show that it's wrong for one thing, then it's enough. All right, so we're out of time. Yeah, and so I'm going to give you some insight into these two statements next time using Venn diagrams. Questions about what we've talked about so far? Yeah, all right. So, well, thanks a lot. I'm going to still post the notes and the video of the class online. And I see you Thursday. Yes.
Thank you, sir.
Have a nice day, everybody.
Thank you.